Okay, welcome back to the second part of our regression lecture. Now what we wanted to discuss is how do we fit our regression model if we have chosen a function which we want to approximate to our data. So the answer you see here is minimize the residual sum of squares. What is that? Now, the fit of a function in regression is measured by the residuals, and the residuals are here the distances of every target value to the corresponding function which we have fitted. So the samples here are the red dots, and the function we fitted is the blue one. And then you see here that we have sometimes small residuals, and sometimes we have a bit larger residuals. And what we do in regression is we sum up all these residuals to the square, and this is then called the residual sum of squares, and we want to minimize this. Okay, so we want to minimize the approximation error of our function f to the values y. And the residual sum of squares from beta is now that we have the residual, which is the target minus our function value for the observation I, and this to the square. Y to the square, we could also take absolute values, but if we take it to the square, then it's easier to optimize because then it's a smooth function. Now let's set in what we already know. So we have seen that our function f can actually be depicted as an inner product of our function phi, of a function phi, which is called a basis function, and a regression vector called beta. And this is what we insert here in the next line. So here we have, instead of f, now we have phi from di transposed, and then the inner product of this with beta. Now we want to write this in a more compact way, and the idea to do this is to gather all these function values of phi in rows of a matrix. So our original data matrix was looking like this. So we had here the observations as rows. And now what we do is we define our matrix X, which has the transformed observations phi as rows. And then this here, the value of phi from di transposed is actually the ith row of our matrix X, and then we insert this here, and then we see that this sum over the squares is actually equal to the squared Euclidean norm of the vector, which is y minus x beta. So this defines here our important parameters for the task of regression, which is the regression vector beta, the target value vector y, and the matrix X, which is our design matrix. Let's have a closer look at the design matrix. So we had our function class for a specific basis function phi, given as the set of all functions which are defined by an inner product of phi times beta. And then we gather the transformed feature vectors phi in the design matrix X and the target values in the vector y. So this is what I just wrote. So here we have our design matrix X, and the rows are the transposed values of phi applied to our observations of our feature vectors. And then the design matrix has here now P transformed features and still n observations. This is of course still the same. And our target value vector has of course still n observations. Okay, now we can formulate the regression task a bit more concrete. So we have again given our data set, which consists of n observations, and then what we have to do is to choose a basis function phi and to create the design matrix. Then we have to find the regression vector beta, which solves the objective to minimize the residual sum of squares from beta. And our result of regression is then the predictor function f, which is defined as the inner product of our basis function phi and the regression parameter vector beta. Okay, so far so good. The only thing which is unclear now is just this step here, right? So how do we find this regression vector beta, and how do we find the minimum of this objective here? Now this is then a task for optimization. So we had in the optimization lecture already the important properties of a function such that we can give some guarantees about the solution we get, and one of these important properties was the convexity or non-convexity of the objective. Now you see here that the residual sum of squares is actually a convex function, which is good because then we know that we will have only one global minimum which we will have to find. Okay, but let's see why that is the case. So the function RSS, given here by this definition, is convex. Why? Now, first of all, we have to show that the squared L2 norm is actually a convex function, which is like the outer function here. And we will not do this here in the lecture video, but you can look it up in the accompanying math PDF. It is not like super straightforward because we cannot apply any of the rules we had. We know that the norm is convex. We know that x squared is convex, but usually the combination of two convex functions is not necessarily convex. So we cannot really say anything by any given rule here. So we just have a look at the actual definition of convexity of a function and then show that this definition holds. If you want, you can look it up. If not, that's also fine. You don't need to know how that goes, but it might be interesting. And when we have shown that the squared L2 norm is actually a convex function, then we know that the residual sum of squares is convex because the composition of an affine function, which is now here g from beta, which is here the inner function, y minus x beta, and the convex function, the norm to the square, is then also convex. This we had in our optimization lecture, that this composition of a convex function and an affine function is also convex. Okay, so we have now here a convex optimization problem, which is to minimize the residual sum of squares of beta subject to beta in r to the power of p. And now, as you might remember, for an optimization problem to be convex, we needed to fulfill two properties, and that is that the objective function is convex and that the feasible set is also convex. And this is here given because the function is convex, as we have shown in the previous slide. Let's assume we have it shown. And the space of r to the power of p is of course convex. So we have an unconstrained optimization problem with a smooth objective function. How do we solve this problem? Yeah, it's Fonk, right. So this is like the perfect setup to apply Fonk and maybe Sonk, but we don't do Sonk here. Now, what was Fonk saying? Fonk said that every local minimizer has to be a stationary point. So to derive our candidates of these minimizers, we compute the stationary points now. And this means that we set the gradient to 0. And now this residual sum of squares function should be maybe a bit familiar to you because we had this function in our optimization lecture, and we have also calculated the gradient in the accompanying math PDF. So if you want to know how that goes, please just look it up. Otherwise, just take it as it is. So we set now this gradient here to 0, and then we have minus 2 times x transpose times y minus x beta is equal to 0. And what we do then is here we divide by 2. So the 2 falls here away from this equation. And then we apply distributivity. So then we have here minus x transpose times y minus times minus is plus x transpose times x beta is equal to 0. And then we add here x transpose times y, and then we have standing here x transpose times x beta is equal to x transpose times y, right? And this is what is standing here. And now we don't really know how to proceed any further, right? Because x transpose x, we can put that to the other side if it would be invertible, but if not, no idea. Okay, so let's just deal with it as it is right now. So according to Fonk, the set of possible minimizers of the regression problem are given by the set of regression vectors, which is defined by this system of linear equations, which is this one here. Okay, So we somehow have to solve this system of linear equations to get our regression vector. And since RSS is convex, all stationary points are global minima. So these are actually our global minima. Now there is no formal proof here anywhere that all stationary points are global minima. It's not super complicated, but it's also not super straightforward. So I'll leave you here with an intuition about this, which is that if you have something else than a local minima, and okay, we already have seen that local minima are global minima for convex functions, right? That was a result of the optimization lecture. And if you have now something else, so a stationary point could also be a saddle point, or it could also be a maximum. But if you have something which looks like this, here, like with the saddle point, then you can always find 2 points for which we have that the function values are larger than the values from one point and another point, from x and y, like here. And this is, according to the definition of convex functions, not possible. And the same holds here for functions which have a maximum. Here's again, the function values are over this linear connection between x and y. And according to convex functions, this cannot be. And this is the reasoning behind this, and in higher dimensionalities it also still holds, but I don't think that a formal proof of this is here not necessary. Now this is nice in a way, right? So we have now the knowledge that all stationary points are global minima, and this is here our set of global minimizers. Okay, so that's cool, because we have here our global minimizers, but the problem is still, how do we get now this better? And if x transpose x is invertible, yeah, then it's nice. So the idea is, when I have x transpose x times beta equal to x transpose times y, then I just multiply with x transpose x to the power of -1, so the inverse of x transpose times x from the left. And then I have here the identity matrix times beta, and the identity matrix times beta is just beta, which is equal to x transpose x, the inverse, times x transpose times y. And this is what is standing here. Okay, nice. But what happens if the matrix x transpose x is not invertible? Well, then there might be infinitely many global minimizers of the RSS from beta. Okay, so an example is here where we fit a polynomial function to these 3 data points here, and every of these functions which are mapped here belong to one beta, and all of these betas are actually global minimizers, and there are infinitely many of these. We might see an example of this in one of the exercises or the homework. Okay, so if we have then this infinitely many global minimizers, then we have a bit of a problem of which we should maybe choose, or if we should maybe choose another function family, maybe a polynomial of a smaller degree or something like that. So to recap, if I have a regression problem, then I choose a basis function and I determine the solution by solving that system of linear equations. I say here the solution, but there might be infinitely many. But the question is now, how do I know if I chose a good basis function, or do I have a good model? Like, is there not maybe something better, or is this okay? And this we will discuss then with the bias variance trade-off, which is a theoretical framework for evaluating regression functions. But this is then a topic for the last part of this lecture. See you then.